Hello everyone. In today's video we're going to be doing a torque balance for a cuvette viscometer, and we're going to go ahead and hop on into this diagram before we start talking about these equations, just so we can get a little background on what the cuvette viscometer is going to do and what we're going to be trying to solve for and why we are trying to solve for it. So basically in this scenario we are going to have two concentric cylinders. We're going to have a smaller one with a smaller radius on the inside of another cylinder with a wider radius, and between these two cylinders there's going to be a Newtonian fluid, alright? And over here on this inside smaller radius cylinder there's going to be a shaft which is going to be torquing the inner cylinder here, causing it to rotate. And what this is going to do is this is going to cause the Newtonian fluid to start to rotate along with the fluid. Now, normally this would also cause the outer cylinder to rotate, but we are going to be doing a torque balance to keep the outer cylinder from moving. Alright, so basically what's going to be happening is the inner cylinder is going to be rotating along with the Newtonian fluid, but our outer cylinder is going to be remaining steady. Alright, and the way the fluid is going to be behaving in this is something called a no-slip boundary condition. That is what's going to be used to describe the behavior of what the fluid is going to be doing. Basically, what the no-slip boundary condition is that it says that the velocity of the liquid is going to be the same as the velocity of the surface that it is in contact with. So basically what that is saying is that the liquid on the very inside touching the inner cylinder is going to be moving at the same speed as the inner cylinder, alright? And the speed at the very outermost edge touching the outside cylinder is not going to be moving at all, right? Because our outer cylinder is not moving. So the velocity is going to be 0 on the very outside. And yeah, so basically the equation that is going to be used to describe the speed in the middle parts where it's not touching the surface is going to be right here. That is going to be our velocity profile equation right here. And this is going to be our shear rate equation right here. And what we're going to be doing is we're going to be using these two equations to prove that the torques on the inner cylinder and the outer cylinder are going to be equal, alright? Alright, so now let's go ahead and start solving for our equation for the torque on the inner cylinder here. And our equation for torque is pretty simple to start out with. Torque is going to be equal to the radius of the inner cylinder, because we're solving for the torque on the inner cylinder first. So that's going to be equal to the radius on the inner circle times the force put out in the perpendicular direction, because the force is going to be perpendicular to the surface of our inner cylinder. And we don't know the force, so we're going to want to substitute this for terms that we do know and we are going to be able to figure out. And we know that our shear stress over here is going to be equal to the force over the area. So we know that force is going to be equal to our shear stress multiplied by the area. So we can go ahead and substitute that in for our torque. So torque is going to be equal to radius of the inner cylinder times shear stress times area. And we know that our shear stress is going to be the same over here. It's going to be our viscosity times our shear rate. So we can go ahead and substitute that in down here and get torque is equal to radius of the inner circle times viscosity times our shear rate times the area. Alright, and this is going to be our equation for torque that we are going to be solving for. So we'll go ahead and erase the rest of this. We're going to write this equation right here so we don't forget it later. Alright, we'll go ahead and erase that now. Now, we do not know the shear rate right here. So what we're going to have to do is we're going to have to solve for it in this equation. And to get there, we are going to have to plug our velocity profile equation in right here. We're going to have to substitute this expression in for VO down here. So pretty much what we are going to be doing is first we're going to be dividing all of this by R. So we are going to pretty much be doing 1 over R. We're going to be solving for this first, right? And pretty much all that is going to do is that is going to get rid of this R expression right here. This is going to turn into a minus 1. And then right here, this is going to turn into a big R squared over an R squared. I should talk a little bit more about this equation first. This little r is going to be the radius of the inner cylinder, and this big R is going to be the radius of the outer circle, or not circle, cylinder, excuse me. And K is pretty much just going to be a ratio of the outer radius to the inner radius. So K is just big R over little r. That's what these K's over here mean. So let's go ahead and do this. So we're going to go, shear rate is going to be equal to R d dr, and then this is just going to be the same as up here with the 1 over R. And we're just going to plug it all in right here. K squared, 1 minus K squared, and then R squared over little r squared minus 1, like so. Alright, and then we're going to need some brackets. Alright, now what we're going to want to do is we're going to want to take a derivative of this expression right here. And this is with relation to little r, so pretty much all we're going to be doing is taking the derivative of this right here, right? And to get that, right here, this 1 is a constant, so that's pretty much just going to be going away right there. We're not going to have to worry about that. Actually, we can just bring it out here to the front, and we're just going to be doing this. So the derivative of 1 over r squared, which is pretty much r to the negative 2, is going to be negative 2 r to the negative 3, right? So this is going to turn into a negative 2 being brought out front, and this is going to turn into an r to the third over here. So let's go ahead and write that out right quick. This is going to be equal to r, then w k squared over 1 minus k squared, and then this is going to be big R squared over R cubed, and then a negative 2, like so. Let's get our parentheses going. We'll just go ahead and rewrite this. This is not what it's supposed to look like. Alright, let's try that one more time. Go ahead and get the brackets going out here again. W k squared over 1 minus k squared. We're going to bring that negative 2 out. And then this is going to be big R cubed, or squared, excuse me, over little r cubed with bracket like so. Alright, and now the next thing we're going to want to do is we're going to want to multiply this r out. So this is going to cancel with that r right there, and we'll go ahead and bring the negative 2 out front. We're going to get sigma is equal to negative 2w k squared over 1 minus k squared over r squared, big R squared, times little r squared, like so. Alright, earlier in the video I made a mistake when describing what this k expression was. Originally I had said it was equal to big R over little r, but it's actually the inverse of that. K is going to be equal to little r over big R over here, right? And so that we can see that K to the negative 1 is going to be equal to R over R, big R over little r. So if we did K to the negative 2, that would turn into R squared over little r squared, which we can see we have right there. So what this is going to allow us to do is substitute in K to the negative 2 over here. We're going to go sigma is equal to negative 2w k squared over 1 minus k squared, and we'll go 1 over k squared. And as you can see right here, these k's are going to cancel out right here, and that's going to leave us with our shear rate being equal to negative 2w over 1 minus k squared, and that is going to be our shear rate for our inner cylinder right here. Negative 2w over 1 minus k squared, like so. And then we're going to go ahead and be able to plug that in up here. So we'll go ahead and erase all this. Erase our k's. Alright, we'll go ahead and plug this in. We'll get a I right here so that we know that we're talking about the torque on our inner cylinder. Ti is going to be equal to negative 2w vi so a over 1 minus k squared. There we go. Alright, so now that we have solved for our shear rate in our torque equation, we are now going to want to solve for our area over here. And that's not going to be as complicated. Our area is simply going to be our area of the circle multiplied by the height of the cylinder. So pretty much it's going to be 2 pi times Ri, which is the radius of this inner circle, times h, which is going to be the height of the cylinder. So our A over here is going to be equal to 2 pi Ri times h. Right here, we'll go ahead and plug that into our torque. Ti is going to be equal to negative 4 pi. And then we got Ri, should be an R right here. Looks more like a V. I'm going to make sure we know that's an R right there. Times our viscosity. And then we have another RIH. RIH, which is going to then turn into an Ri squared. So we'll just go Ri squared times viscosity H, and then that is all going to be over 1 minus k squared. And there you have it. That is going to be our expression for the torque on our inner cylinder. And now we are going to solve for our torque on the outer cylinder, and we are going to want to see that the two expressions for the two torques are going to be the same. Alright, so to go ahead and solve for our outer torque, we are going to use the expression that we solved earlier for our shear rate, and we're just going to be changing around to fit the new outer cylinder parameters. So our expression for that was shear rate was equal to negative 2w, and then it was k squared over 1 minus k squared. Right, and then over here we had our big R squared over our Ri squared. And pretty much the only difference between the shear rate at our inner cylinder and our shear rate at our outer cylinder is going to be this parameter right here. This Ri is going to turn into just big R right here, because we're now looking at the radius of the outer cylinder, which is going to be equal to big R. So right here, these two terms are simply just going to cancel out. So our new sigma, our sigma for outer, is going to be equal to negative 2w k squared over 1 minus k squared, like so. And this was our shear rate for the inner right here. We're not going to need that anymore, so we'll go ahead and erase that. All right, and now we can use this to go ahead and solve for our torque at the outer circle, or cylinder, excuse me. So our T at the outer is going to be equal to, again, this is going to be big R this time, multiplied by the viscosity. And then we are going to have this expression right here for our shear rate. This is going to be negative 2w k squared over 1 minus k squared, like so. And then, as you can see over here, our area is pretty much going to be the same as right here, except we're going to be using big R again. So it's going to be 2 pi times big RH. We'll go ahead and simplify this out a little bit, make it look cleaner. This is going to be negative 4 pi, and then big R squared, sigma H times negative 2w k squared over 1 minus k squared. All right, there you have it. We'll go ahead and simplify this further. We'll do TO is going to be equal to negative 4 pi times viscosity times the height. We'll put that all over 1 minus k squared. And then we will bring our r squared, our big R squared, and our k squared out here. R squared, k squared. Now earlier, again, we said that k squared would be equal to our ri squared over our big R squared, r being the radius of the outer cylinder and our ri being the radius of the inner cylinder, right? So if we go ahead and multiply our big R over to this side, we would get that our inner radius squared would be equal to k squared times r squared. And if you look over here, we have that exact expression right here. So we can go ahead and substitute ri squared in for this big R squared times k squared over here. So we'll go ahead and do that. And that would give us the torque on our outer is equal to negative 4 pi, then times ri squared times viscosity times height over 1 minus k squared. And there you have it. As you can see, our torques on our inner cylinder and the torque on our outer cylinder is going to be exactly the same. It's the exact same expression. And pretty much what this means is that our equations up here are valid. We are going to be able to use these to represent the velocity of the Newtonian liquids between the cylinders at a given radius, all right? And again, the radius is going to be highest at the inner cylinder, and it's going to go down as you get closer and closer to the outer radius of the outer cylinder, where the velocity is going to be 0, the same as the velocity of our outer cylinder, right? Because our outer cylinder is not moving. And because these equations are valid, this is going to allow us to determine the viscosity of the liquid, which is pretty much just the inner friction of the liquid, basically meaning like how sticky and how thick that liquid is. And that is going to be the purpose of this device, is to determine the viscosity of the liquid between it. And there you have it. That is going to be all for today's video. I hope you guys enjoyed, and I hope you guys will like and subscribe and watch more videos if you enjoyed this one, and have a good day.